Today we'll continue with the topic on coastal water level fluctuation. This animation here shows a coastal tsunami. As we all may be well aware, that tsunami are generated due to undersea seismic activity. Now, tsunami wave may have a periodicity of 5 to 60 minutes, which means they are much longer than the wind waves. However, that is still much shorter than the periodicity of tides. Now, if we look at the tsunami wave in the ocean, actually they have relatively low amplitude, and because of its long wave length, so it has a low steepness in the ocean. So for example, if there is a boat in the ocean and the tsunami wave pass by, the boat may or may not even notice. However, as this tsunami wave approaches the shoreline, it undergoes refraction and also shoaling. And as we recall what we learned about shoaling effect, it causes the wave energy to be concentrated in shorter and shorter wavelength, and increasing the wave height at the same time. So which is why when we observe tsunami, or when tsunami hit the shoreline, typically they have very large wave height, and as a result of that, they are able to run up landwards, in some cases even kilometers landwards, causing massive destruction because of the energy that it carries. We need to remember that because of the long wavelengths, so tsunami actually behave more like the tide than the wind wave, meaning that their oscillatory motion actually is able to reach all the way down to even the ocean floor. So the energy occupies the entire water column, which is why when they arrive at the shoreline, all this energy get focused together and become highly destructive. This figure here shows example of water depth in the ocean and the wavelength of a tsunami, and how this wavelength changes when it approaches the shoreline, and how the amplitude of the wave increases as the tsunami approaches more and more shallow water. So for example, we may have a tsunami with a wavelength of up to almost 300 kilometers in the deep ocean, moving at very high speed, up to 900 over kilometer per hour. And this evolves to, for example, only a wavelength of 48 in water of 200 meter deep, but the velocity has reduced, and eventually when the water depth drop to 10, and the wavelength may become so short, it's only 10 meter, and the velocity now has greatly reduced to only about 36 kilometer per hour, and that concentration of energy causes the wave height to increase. This figure here shows example of a tidal gauge record. We have mentioned about how the tidal gauge measures the water level in the coastal area. So here it is an event which happens in 1960, is in Hawaii. So this will be the normal tidal water level fluctuation, and when the tsunami arrives, we see that the water level increases significantly compared to the regular changes, and after that there's a second wave and third wave, so on. Of course, the water level goes up and down in this case, and you can imagine the kind of damage that such a high increase of water mass of water moving towards the shoreline can create. Ever since the recent 2004 Indian Ocean tsunami, which affected many countries in the Indian Ocean, and also the tsunami in Japan, so the world are increasingly educated and aware about the destructive force of tsunami. So engineers has been designing or looking into various tsunami protection design, which of course is very costly, and is a huge engineering challenge. And of course, the problem is tsunami only happens rarely. So to invest into this kind of facilities is very not cost effective. However, we also found out that the natural coastal ecosystem can actually provide tsunami protection to a certain degree, such as the wall of mangrove, which are able to absorb the force of a tsunami and help reduce the damages. Now we know that the mangroves have very interesting root structure that hold on to the seabed, and laboratory test has been carried out to look at how the wave transmission through a series of reed. In this case, for example, what we are looking here is a study which look at the effect of this reed or bakau or mangrove type of growth in the coastal region, how this reed um, is able to reduce the wave transmission. So we have HT, the transmitted wave height, over HI, the incidence wave height. So that is basically the transmission coefficient, if you recall what we study in wave mechanics. So as the width B increases, we can see that the transmission coefficient drop. So without the coastal reed like this, then we have a transmission coefficient of 1. That means that all the incidence wave height will be able to reach the shore. But if we have a reed as wide as 5 meter or 10 meter, for example, we can see how it drops, and this depends on n. N here actually refers to the density of the reed or the root structure. Okay, we have for example 50 per meter square, 50 of this root structure per meter square, or up to 400 per meter square. So the higher the density, we notice that the transmission coefficient drop much faster compared to 50 or 100 over here. And if we have a growth of 20 meter wide up to a density of 400 per meter square, you notice that actually we can reduce the transmission to as low as only 0.1, which means 10% of the incoming wave. So that is one of the natural way, and also highly aesthetic. And besides, mangrove or reed like this is very good for the coastal ecosystem. So this is a natural way of protection that we can consider, but of course the approach is not always applicable to the developed coastal area or sandy beach area, but engineers need to be creative in finding solutions. You can research further online on what are the most state-of-the-art development in some proposed tsunami protection technology around the world. So other than looking at the wave transmission, the run-up, the landward travel of the tsunami, one of the important aspects of tsunami warning is actually to estimate the arrival time. Of course, to estimate the arrival time is so that we are able to give ample time for people to evacuate the coastal band. It doesn't change the fact that it's going to cause the destruction, but it is able to save lives. Now, travel time of tsunami can be estimated based on the assumption that tsunami is a long wave, so it travels as shallow water wave. So if you recall that for shallow water wave, the wave celerity is given by square root of gd. D is the water depth. So if that is the speed that tsunami wave is traveling, then that means the time for the tsunami to travel a distance s will be given by s divided by the celerity. Okay, time is given by distance over velocity. However, the depth changes when the tsunami travel from the ocean to the coastal area. So as this value changes, the celerity changes. So in order to more accurately estimate the arrival time or the time taken for the tsunami to travel from its source to a particular coastal area, then we will have to break down the distance that the tsunami travel into incremental section, and for each incremental length we will use the average depth of that length in order to estimate the time to travel that particular segment, and eventually we sum up all the time for the individual segment to get the total travel time. For example, over here we're looking at the Pacific Ocean. We have the tsunami that originates somewhere here in the middle of the ocean. So this tsunami will travel out in the all direction, hitting the shoreline in the American continent, the Asian continent, and also Australia, even New Zealand over here. So in order to estimate the time of arrival of the tsunami wave, for example, here in Malaysia, we want to know when the tsunami is going to hit us. So what we can do is that we can apply this equation, right? We can subdivide the distance traveled by the tsunami to our shoreline into segment, right? For example, each of these may be in the order of 100-kilometer distance, so S. So each of these is for example, 1,000 kilometer, for example. And then for each of these segments, what is the depth? So if we know the distance, if we know the depth, we know the celerity, we can calculate the time for the tsunami to travel from one end to the other end of this segment. And after that, we do the same again for the next segment, the distance and the depth to estimate the time. And so as we proceed, we are able to get what is the total time it takes for this tsunami wave to arrive at, for example, Terengganu on the eastern coastline of peninsular Malaysia. Now let's look at this example. One of the waves in a tsunami has a period of 20 minutes and a height of 0.6 meter at a point in the ocean where the depth is 3,800 meter. Determine the celerity and length of this wave. Okay, we'll stop here. So now we're going to look at this tsunami at a location somewhere in the ocean which has a water depth of 3,800 meter. Now, although it is a very deep location, but for tsunami it is still shallow water because the tsunami energy occupies the entire water column. So we apply the equation C equals the square root of GD for the celerity of a shallow water wave, and we found out that the tsunami is moving at a speed of 193 meters per second, which is equivalent to about 700 kilometers per hour. That's really, really fast. And if you look at the tsunami itself, is actually only 0.6 meter high, which means that if you are on a boat in this location in the deep ocean, your boat will just go up and down by 0.6 meter. You can hardly even feel it. And 20 minutes later, the same tsunami, the second wave will pass you by again, and your boat probably will just go up and down again by 0.6 meter. You didn't even realize that the tsunami has just passed you by. Now what about wavelength? If we calculate wavelength, the tsunami has wavelength here, which is about 232 kilometer. So you can cross-check this value that you just obtained for in this example with the table we see earlier. Of course, they won't be the same because every tsunami is unique, but depending on the wave period and also the initial wave height, so we can get a sense of what is the tsunami like when it is still in the ocean. If we check the DOL value, it's about 0.016. If we check the wave steepness, you notice that for wave steepness here, actually this should be, the wave height should be only 0.6 meter, so should be 0.6 meter divided by this wavelength. So the value is very, very small. Right now, let's move on to look at how the tsunami wave behave in the nearshore region. The question here says that determine its celerity, length, and height in a nearshore depth of 10 meter, assuming no reflection, diffraction, or reflection effects. Now, after we ignore all these three wave transformation effects, remember that we must still consider shoaling effect. Shoaling effect always happen because it is due to the change of water depth. So in order to consider that, we just want to make a quick recap about shoaling. Remember that N times E is a constant. E is the wave energy given by this expression. N is the ratio of the group celerity to the wave celerity. So if we substitute this expression inside, we should get something like this, and we can rearrange it into this form and eventually write it in this expression, which will allow us to find out what is the wave height in the nearshore region compared to the wave height in deep water. Of course, here we have the for the shoaling coefficient, we have the complete expression looks like this. It will take into consideration the change of the wavelength from deep water to the shallow water region. It will take into consideration the change of N value. But remember, the N value in deep water is 0.5, whereas in shallow water is 1. So the N value would have changed. But for the case of tsunami, since tsunami behave as shallow water from the source and up to the shoreline, so that means for tsunami the N value is the same all the time. The N value equals to 1 for a shallow water wave. Okay, so if there's no change in shallow water wave, then that means the change in the wave height of tsunami only depends on the change of its wave length. And since the change of the wave length for tsunami is dependent on the change of the water depth, so we can then apply the equation accordingly to solve using the equation for shoaling effect. But let's look at how the solution here does it. Okay, so basically we arrive something like this, which basically is this one, isn't it? N has already dropped out because N is the same in both locations. So now we have h squared L at the water depth of 10 meter equals to h squared L at the water depth of 3,800 meter. So it's basically from here. The deep water wave height is 0.6. What we're interested here will be the shallow water wave height. So we need the wavelength. Now since tsunami behave as shallow water, So the wavelength can be given by this expression. Wavelength is equals to c, which is the wave celerity, times t, and the celerity depends on the water depth. So instead of solving this, you notice the solution here, substitute this into the equation, so you get this expression instead. After substituting this expression into here, basically the square root of g cancels out, the wave period also cancels out, so what we are left with is this expression. Okay, so now we can rearrange this equation into this form, where h is on the left hand side. So we found out that if now we substitute the water depth into the equation and the deep water wave height of 0.6, then the wave height at 10 meter is now 2.65 meter. So since we are able to apply c equals to square root of gd, so we can also find out what is the celerity. The celerity has now reduced to only 9.9 meter per second compared to more than 700, about 700 kilometer per hour previously, and the wavelength has now reduced to about 12 kilometer compared to about 300 kilometer previously. So overall, the shoaling effect has increased the wave height by a factor of 4.4 times in this particular case. All right, and of course we have ignored all these other effects which may increase or decrease the wave height depending on the local bathymetry, local shoreline geometry.